At sunset, the ocean darkens from above, and an immense living traffic stream begins rising through the twilight zone. The travelers leave no road, yet their synchronized movement can reshape food webs, carbon flow, and the ocean's nightly soundscape. This is Diel vertical migration, a repeated ascent towards surface food, followed by retreat into darker daytime refuge. It spans many seas and countless animals, although timing, distance, and direction change with place and season. If you hovered at 300 meters, scattered flashes and moving shadows would gradually thicken around you. Lanternfishes, bristlemouths, krill, copepods, squid, and gelatinous predators participate, each following different risks and rewards. Some climb hundreds of meters, some shift only modestly, and others remain while their prey passes overhead. The highway is therefore not a single lane, but overlapping migrations revealed by nets, acoustics, cameras, and biochemical evidence. Dominant rhythm is light, measured not by human clocks, but by the fading and returning sky. As illumination weakens, visual hunters lose range, reducing danger for small animals entering food-rich upper water. Before dawn restores that danger, many migrants turn downward and vanish beneath the brightening surface layer. The mystery is how billions of individual decisions become the largest recurring animal movement commonly described on Earth. No leader directs it, and no traveler perceives the ocean-wide pattern created by countless local responses. To follow this hidden migration, we must track changing light, feeding opportunity, predator vision, and physiological cost together. The journey starts in a zone defined less by fixed depth than by rapidly diminishing sunlight. Oceanographers commonly place the mesopelagic between roughly 200 and 1,000 meters, with regional variation. Enough light penetrates its upper reaches for sensitive eyes, but not enough to support meaningful photosynthesis. Temperature often falls through this layer, while pressure rises, and oxygen can decline sharply in certain regions. These gradients divide the highway into habitats whose boundaries shift with currents, weather, productivity, and climate. Many lanternfishes have large eyes and light-producing photophores, adaptations suited to dim water and visual signaling or camouflage. Counter-illumination can reduce a silhouette by matching faint, downwelling light, though effectiveness depends on angle and conditions. When surface light fades, upward movement improves access to copepods, krill, and other concentrated planktonic food. Feeding near the surface stores energy, while descent at dawn reduces exposure to birds, tunas, and other visual predators. This cue-action adaptation consequence sequence explains much migration, but it does not fit every species or every night. Cloud cover, moonlight, sea ice, turbidity, and artificial illumination can alter how animals interpret their luminous environment. During bright moonlit nights, some migrants remain deeper or adjust timing, consistent with avoiding improved predator vision. Direct acoustic observations show scattering layers rising after sunset and sinking near dawn across many ocean regions. Sound reflects from gas-filled swim bladders and animal tissues, producing bands that early sonar operators mistook for seafloor. Acoustic strength indicates aggregated organisms, not exact species, abundance, or body size, without careful calibration and sampling. Net catches identify residents and migrants, yet nets can miss fragile gelatinous animals and fast swimmers. Cameras preserve behavior and body form, but their lights may attract, repel, or alter the animals being recorded. Combining these methods narrows interpretation while leaving vast stretches of the migration highway unobserved. Bristlemouth fishes of the genus Cyclothone are extraordinarily numerous components of many midwater communities. Their abundance does not mean every individual migrates, because related species and life stages occupy different depths. Krill may ascend to graze phytoplankton or capture small prey, then descend with carbon-rich material inside their bodies. Copepods can join daily movements, while some also enter seasonal dormancy at depth after storing lipids. Squid follow prey upward, using rapid swimming and sensitive vision, and become prey for fishes, seabirds, and mammals. Gelatinous predators drift or swim within these layers, intercepting migrants with tentacles rather than chasing them across long distances. The clearest evidence appears as motion, but the highway's importance emerges from what travelers carry. At the surface, a fish consumes carbon that phytoplankton recently fixed using sunlight and dissolved carbon dioxide. At depth, respiration releases some carbon, waste particles sink, and predation transfers material into another body. This active transport supplements passive sinking by moving carbon downward before digestion and excretion are completed. Its magnitude remains uncertain because migration distances, biomass, metabolism, and mortality vary across regions. Estimates built from acoustics require assumptions about which organisms produced echoes and how strongly each reflected sound. Net-based estimates require corrections for avoidance, damaged specimens, incomplete depth coverage, and patchy distribution. You can see why a bright acoustic band is compelling, but it cannot alone measure carbon delivered below. Researchers compare day and night depth profiles, stomach contents, respiration models, and particle chemistry to constrain the flux. Even then, a migrant may release carbon at one depth and return nutrients upward on another journey. The highway is a biological pump with branching exits, recycling loops, and passengers that change through life. Larvae may remain shallower than adults, while growing fish acquire swimming capacity and different vulnerability to predators. Hungry animals may accept brighter water, whereas well-fed individuals can remain safely below and conserve energy. Predators also migrate, producing a moving landscape of fear rather than a simple escape from fixed enemies. When prey rises, hunting squid and fish follow. When daylight returns, both groups must balance concealment against feeding. Some deep predators wait at the route's edge, turning predictable traffic into a nightly feeding opportunity. This creates a behavioral cascade. Light shifts, prey ascends, predators reposition, and carbon changes hands. Oxygen minimum zones complicate the route by compressing animals into layers where respiration remains physiologically possible. Species tolerant of low oxygen may occupy refuge water that excludes less tolerant hunters. Others cross depleted layers briefly using efficient oxygen transport. Reduced activity or metabolic flexibility. Warming can increase metabolic demand while reducing oxygen solubility, potentially changing costs along the vertical route. Consequences are not uniform because circulation and biological production control oxygen patterns region by region. Acidification also changes seawater chemistry, with uncertain effects across the varied organisms, forming scattering layers. Fragile pteropod shells are vulnerable to reduced carbonate availability, while fishes face different physiological challenges. Evidence for community change must separate long-term trends from seasons, currents, instrument differences, and natural variability. The highway looks continuous on an ocean map, but local interruptions can redirect or narrow its traffic. Seamounts, continental slopes, fronts, and eddies concentrate migrants and attract larger predators to predictable locations. That connection carries twilight zone energy into surface fisheries, deep benthic communities, and wide-ranging marine mammals. Tunas and billfishes may dive into mesopelagic layers, constrained by temperature, oxygen, pressure, and prey distribution. Some whales target deep scattering layers, converting small midwater animals into energy for enormous bodies. Commercial interest in mesopelagic fish has grown because their collective biomass may be substantial. However, biomass estimates differ widely, and acoustic models cannot simply be converted into harvestable stock. Many midwater fishes grow slowly, mature at different ages, and occupy food web roles that remain incompletely resolved. Removing them could reduce prey for predators and alter carbon transport, even if catches appeared small against global estimates. Management would require species-level knowledge, regional population structure, bycatch assessment, and reliable monitoring at depth. The migration highway also intersects fishing lines, nets, ship noise, and expanding artificial light near coasts. Light from vessels can reorganize vertical distributions, potentially changing catchability and behavior during scientific surveys. Climate-driven stratification may reduce nutrient delivery to sunlit waters, altering the surface food that motivates ascent. If productivity shifts geographically, travelers may change routes, timing, body condition, or reproductive success. These responses could influence how much carbon reaches depth, creating feedbacks that models still represent imperfectly. At dusk, a copepod responds to fading light, rises to feed, escapes one predator, and may nourish another. A lanternfish detects prey, flashes beneath it, strikes, then descends carrying the meal beyond the morning-lit layer. A squid follows moving targets upward, accelerates through thin light, and becomes visible to a diving hunter. Each sequence is documented in principle, while exact encounters remain hidden within a vast three-dimensional night. Together, they form an ecological transport network powered by appetite, fear, darkness, and evolved sensory limits. Future evidence must follow identifiable animals through complete cycles instead of inferring every movement from a shifting layer. The stakes lie in protecting this transport system before harvesting, warming, and deoxygenation alter routes that remain poorly understood. Future long-duration acoustic observatories can compare migrations across moon phases, seasons, oxygen changes, and extreme weather. Wheater, low-light imaging can test behavior without overwhelming the faint cues animals normally use. Stratified net catches may identify species at selected depths, but they cannot prove every animal's direction or migration route. Better physiological measurements can constrain respiration and excretion under the pressure, temperature, and oxygen encountered during travel. You would then connect movement to carbon transport with fewer assumptions between an echo and a calculated flux. Repeated surveys are essential because one spectacular night may not represent a season or an ecosystem. Comparisons among productive upwelling zones, oligotrophic gyres, polar seas, and continental margins will reveal different highway designs. Models must preserve that diversity, instead of forcing every traveler into one average ascent and descent. The most decisive evidence will unite identity, biomass, movement, metabolism, and predation across the same water column. Until then, global totals should remain ranges, and proposed exploitation should acknowledge ecological uncertainty. Yet the central observation is secure. Countless midwater animals reorganize their vertical world as daylight changes. Their nightly decisions feed predators, redistribute elements, and connect sunlight with habitats far below photosynthesis. As dawn approaches, the moving echoes bend downward, and the busy water above becomes deceptively clear again. You are left over a quiet surface, while Earth's hidden migration highway settles into darkness beneath it. The twilight zone's traffic is real, but its full influence remains measurable only through patient, species-aware observation.